our master of ceremonies is not here, so I'm going to have to MC. All right, so this is lecture number 4 of 5, right? Session.
Yes. Unless I invent something else.
Exactly. Unless the lecture 4 of at least 5. But this lecture, you all notice this interesting object. This is a man of his word. So you brought, this is, I assume, a very fancy wine.
I don't know what's it's something I selected
okay, very good.
online, and it's sent to me from Argentina, excellent. From high altitude vineyard.
Okay, very good. Okay, so this goes,
not that it is the most expensive one, it's just the one which I like.
Wonderful. So this is goes to the person with the hardest, most relevant, brutal question today. Right?
I didn't say brutal.
You didn't say brutal.
I would say ignorant. You know, which makes me feel vulnerable or excited, that kind of thing.
Perfect. Very good. All right. Okay. Take it away, sir.
Okay. So it is lecture 4. In the previous lecture, I introduced the Hodge dual surface, which is a geometric analog of instantons. That's something which should have been done, I would say, 40 years ago, because that's a very natural thing to do. Area derivatives were known for 15 years. Instantons were known also for 15 years. You're just putting one and another together. But it's something very, very important for this theory which I'm describing, which I call geometric theory, geometric QCD. And later, on the next lecture, which will be the final, I will introduce twisters, which makes this Hodge dual surface very natural, mathematically beautiful, and tractable. And that will be the most important part. That's something which I hope you'll like most, because that's beautiful mathematics, close to what you hear around, what is resonating in these walls. And also it produces a spectrum which is remarkably similar to what we see in nature. Similar to a 95% statistical accuracy of description of the particle data group. Some of them, 3 trajectories, anyway. So I'm not going to talk about that today. That will be the next lecture. But today I'm going to introduce the most important ingredients, which I call ELFs, or elementary fermions. Okay, before that, I will tell what exactly I'm going to talk about. There will be this ELF theory, which is Majorana fermions on the surface with certain boundary conditions. And there will be what they call conformal gauge invariance. Turns out on 2-dimensional, the determinant of the Majorana fermions depend on the conformal metric, and you could introduce some scaling factors in that conformal metric, and there is something which I describe as gauge invariance. You could make it either the theory of fermions on a flat surface, or with certain anomalous term in the Lagrangian, or the theory of the fermions on a curved surface with appropriate Dirac operator on a curved surface. Remarkable symmetry following for monomers. That's one theme. Another is that this particular system, Majorana fermions on a surface, specifically on a Hodge dual surface, can be reproduced as summing planar graphs. Turns out that because of the Pauli principle for fermions in 2 dimensions, their trajectories cannot really intersect, and therefore summing over paths on a 2-dimensional surface can be related to the planar graph. And that's a very important thing, which came to my mind 45 years ago, but then it was buried because Polyakov, my good friend, anomaly on the 2-dimensional surface killed the whole theory. But now I throw away anomaly and the theory got revived. So I will tell you all about that, about this constellation of intersection of trajectories, and how planar graphs are obtained from these trapped fermionic loops. And then I will talk about how technically the loop equations are reproduced by this Fermion determinant. So that's going to be, I'm going to talk about all the three things because it makes no sense to choose. I'm just telling you the steps. Hope I will have time for that. And if not, I'll just take more time. So we start with the health theory as by itself, without a possible relation to planar graphs of QCD. So we introduce the fermionic field. Could you see that small print?
Yeah.
Okay, fine. Because I see it well. Okay. So it is Majorana fermion, but it's two components. So it's two Majorana fermions. You may say it's not direct because it's two-dimensional. So it's two Majorana fermions. So alpha is a spinor in 1 and 2, and lambda is plus minus 1. That will count the chirality. There will be two kinds of different chiral conditions. So the simplest form of the action is very, very simple. Two-dimensional integral over, say, unit disk. And then there is this two Pauli matrices and derivatives. And then there is this conformal factor, which effectively changes the mass. So it's a theory of the fermions on the flat two-dimensional disk with variable mass. So I made some transformations which put all the metric, and E is this induced metric, in conformal gauge, I put it metric in the mass. That's because of conformal invariance of that action, you actually could transform it out up to anomalies. So at the moment, I'm considering the action of the fermions with variable mass. Because of induced metrics, mass effectively depends on the point. Now, that system has very nice special properties which make it very similar to Ising model on the surface. Not quite, because there are two components. Ising model is only one component. So if you know what is Ising model, it's one Majorana. Here we have oriented loop, so we need to. Anyway, here are these boundary conditions. So the lambda basically is eigenvalue of the sigma 3 operator, sigma 1 and sigma 2 operate here in the Dirac, and sigma 3 is like gamma 5 matrix. So these fermions are chiral. On the boundary, they have chiral boundary. And later you will see the reason why do you need this boundary. At the moment, we just describe this theory as it is. Now, we want to move from flat surface to rigid minimal surface, because that's what we eventually want to do. But that's not so trivial. If there is a metric on the surface which is diagonal, this exponential of 2 rho, where rho is, well, exponential of 2 rho is this conformal metric. So then, of course, there will be spinor connections because spinor particles feel the geometry a little bit, but they feel it. So there will be, and there will be also a very important term, which I will derive later, the anomaly Liouville kinetic term. And that term comes from basically transformation of the integration measure. Or if you integrate for fermions, you will have the Dirac operator, and when you try to eliminate the metric by conformal transformation of Dirac operator, that Dirac operator has conformal anomaly, which leads to this term. That's something which I'm going to describe later. So the theorem, the result, is that there is this action which depends on this conformal metric rho, this one, and if you add the Liouville kinetic term, then that theory does not depend on rho. Rho is like gauge parameter. You could change it. You could take rho equals 0, in which case you will have flat surface, or you could take rho equals logarithm of this conformal metric, and then it will be this theory of fermions living on the curved metric, and there will be a difference between, of course, these theories, and that difference results in this kinetic truth. Okay, so let's consider that. Let's kind of prove, or at least explain how that can be proven. So let's consider these fermions on a curved minimal surface, and we claim that they are equivalent to the fermions on a flat surface with a variable mass. There are two formulations of the same theory. So here is the action of the general theory. It involves kinetic energy of fermions. It involves the mass term, and there is this exponential of rho, which acts like a gauge parameter. You could introduce it here, you could use it here, and add it here. So, these covariant derivatives are ordinary derivatives plus spinor connections times sigma 3. And spinor connection is just curl of this two-dimensional curl of this rho. And that is a standard thing for two-dimensional geometry. It's a textbook thing. So you use Einbein, and then there's the curvature tensor, which is covariant, commutative of the derivatives. And when you do that, you will get this curvature R, which is related to Laplacian of this rho. And integral of curvature, of course, as everybody knows, in two-dimensional gravity is just a Euler number, which is non-dynamical thing in two-dimensional case. It's Einstein theory where Einstein action is topology. Okay, so at rho equals 0, it's an old action, A naught. And if we take rho as logarithm of square root of E, then the mass term becomes the ordinary mass term. Rho disappears. Mass term becomes what is supposed to have for the massive particle in curved space. So if you take rho like logarithm of square root of E, you will get ordinary two-dimensional theory of massive fermion on a curved space. It's some basically general covariant theory of two-dimensional fermions. And if you take rho equal 0, then all these curvature and covariants disappear, you have a flat surface, and then you have different thing, fermions with variable mass. And these two things I'm going to prove you are related. And once they are related, we would use theory of fermions with variable mass to prove equivalence to the loop equations, and then we switch back to the theory of massive fermions on a curved surface, and then we say that is our result. Then we tend mass to infinity. That would make delta function in MM equation infinitely local, real delta function. Otherwise, it would have a width mass. So when we tend mass to infinity, we recover local limit of the QCD, and that's the most important result. So before doing that, let me describe why this rho acts as a gauge parameter, why the theory doesn't depend on this rho. Okay. So first of all, let me just remind you, like I had to remind to myself, what exactly is the two-dimensional Dirac operator on a curved surface. There is this Einbein, and then there is this, in general, there is this connectivity, but in one-dimensional connectivity can be expressed, in general, that's some vector object which is related to metric, blah, blah, blah. But in two-dimensional case, it is just curl of logarithm of conformal metric, and that is basically providing all you need for the general covariance. So two dimensions, as people know, of course, the general relativity reduces triviality. Topology, I would say, not triviality. Anyway, that is what happens with the covariant derivative in two dimensions. And how do we prove that this rho is a gauge variable? Very simple. you try to eliminate it. You make transformation. You have this Dirac operator, and rho is involved there, and then you find out that this rho is basically multiplies exponential of rho multiplies Dirac operator on both sides. You say, okay, I want to rescale operator by these factors, e minus 3/2 rho times e minus 1/2 rho, and technically, naively, that is what will eliminate rho from equation by conformal transformation of coordinates, etc. But when you do that, you have to keep track of anomaly. If you multiply operator by factor, then there are some zeta functions to count for changing in determinant, and also there are some terms which would involve this operator acting on this factor, because this factor depends on the coordinate. So when you do all that, you do quite familiar computations in the WKB approximation of determinant. And what happens when you find variation of determinant? You use what's called Pauli-Villar's regularization of this trace logarithm. And when you do that, you find in the end this remarkable formula that variation of trace logarithm of square of Dirac operator is equivalent to the integral, which after all computation involves universal term, which is some constant, and there is minus curvature divided by 12. So that's what happens if you do the limit of the Pauli-Villars or use zeta regularization. There are many ways to derive it, but all of these ways reduce to the same thing. It's universal anomalous term, which is proportional to the curvature. So variation with respect to rho gives you curvature. So all we need to do, if we want to compensate that, is to find another term, variation of which also reduces to the curvature with opposite sign. And when you do that, we find this Liouville term. So this term minus exponential of 2 rho times curvature is exactly compensated by variation of this Liouville term, this one. So once you have this, if you take variation, you will get exactly this term with the curve. So that's very interesting. We found the effective action, which in view of anomaly does not depend on rho. So the theory does not depend on rho, and that is just a fancy way of formulating something well known. Because nobody really was interested in the theory of fermions with mass, with variable mass. But computation of anomalies of the fermion operator actually says, okay, you can then consider the theory determinant as a theory of fermions with variable mass if you don't forget to add this anomalous term, because that's all the difference. Okay, now we are coming to the interesting place, which is really dynamics. So let's consider this Dirac determinant. We have this integrating over fermions. There are the plus and the minus components. They're independent, and we have a product of two determinants. And that product, each one of these determinants is equivalent to sum over all paths. Okay? Actually, it's not quite sum over all paths. Exponential of trace of log is sum over all paths. But when you put it down, you will have sum of multiple paths. Because in exponential, you have sum of one trace, one closed path. But when you bring it down, you will have multiple paths. And these multiple paths kind of don't care about each other because it's just exponential of one sum over paths. So there will be, if you expand exponential, you get multiple sum over paths which go without caring of each other. However, there is remarkable topological identity which proves that the same determinant can be written as a sum over self-avoiding paths, which, if you think about that, is natural because Majorana fermions don't like each other. Indeed, the trajectories, if you think about the determinant as a path integral, then these paths cannot go to the same point. They
This
must
is the
repel.
same as Feynman's picture. This is in 2 dimensions, right?
Yes.
So Feynman had a path-integral picture for fermions in 2 dimensions with doing for massless fermions in 2 dimensions by summing over the sort of 45-degree.
Yeah, but it's not that thing.
It's not
It's not much. No, the first person who did it was a person who I knew in London, Institute, Natasha Vdovichenko. Everybody knows her last name, but not everybody knows that her name was Natasha. She was a woman. She was very humble young lady, very talented. She was wife of a person who was much more famous in London. And now nobody remembers him. But she invented remarkable proof of the solution of Ising model. She literally said that if you take sum over all the composition of the plane into positive spin region and negative spin region, and by definition, the regions of given span are bounded by self-avoiding curve. So if you do that, then she said, then she honestly compared these curves with the trace of the fermion, and then she found out there is topological identity which makes them. So I will explain that now. It's very intuitive and very simple. First of all, let's remember the Gauss-Bonnet theorem. If you follow the path of any particle, doesn't matter fermion or not fermion. If you take the particle, the closed loop on a plane, actually it could be the plane with an arbitrary number of holes, doesn't matter. You just sit on this particle. You're totally blind, but you are sensitive to rotation of your direction. So you count how many times you rotated around yourself. And you don't care whether you passed the hole or you passed whatever. If you just count the rotations and come back after certain integer number of rotations, you could find out how many times you intersected yourself. So that's called topological theory. So basically, if you, in complex analysis, it's a very well-known thing. If you go around and made integer number of circles, you inevitably intersect yourself corresponding number of times. That's a theorem. There is a theorem which relates Gauss-Bonnet to the index of intersection. And it was studied by separate places in mathematics. It's not exactly Gauss-Bonnet. Gauss-Bonnet is something else, but if you combine it with the theory which counts intersections, I forgot the name of that guy. I just prefer Gauss. Anyway, well, that is the correct state. Sum over delta angles or all path integral or sum, it could be continuum path with infinitesimal changes, or it could be rotations like 45, whatever. It is always topologically 2 pi times 1 minus nu modulo 2 pi. And that's all we care about. So now let's look at that at this path. So let's consider some point where 2 paths intersect. There are 2 planar intersections. So let's consider our oriented paths, right? So if there are 2 incoming and 2 outcoming, and they are like that, separated by the each other. So the 2 incoming are on opposite side, and then there are 2 outcoming. So there are 2 planar intersections. So these are not intersections. The paths are just passing each other without colliding, and they don't intersect topologically, okay? But then if there is a different configuration, like 2 points came here and they came as opposite direction, there is one way to go by and not intersect, it's like that. But another way to achieve the same final state would be to intersect. Now, the claim is that because each intersection carries negative sign, if you think about the whole pattern of all the paths, whenever you compare the whole complex set of paths, the path where at this point, these 2 paths intersect would have an extra negative sign. And the rest of the factors in all these paths would be equal. Even though the mass is variable, this factor is local. All the other factors will have exponential of total length measured with this variable matrix, but that does not matter. They, at given configuration of lines, these two lines which collided at one point differ only by the way these paths went, whether they intersected or not. And if they intersected, the rest of the factors in these lines which continue would be the same as before, but there will be minus sign. That means that these two paths canceled each other. Exactly canceled. It's zero. And these two doubled, not canceled. I mean, they both remained. So the planar, the planar graphs remained and the non-planar canceled. Think about that. They canceled because of the Pauli principle. That's the way to formulate Pauli principle in terms of paths. You add one more dimension, but the principle is the same. Okay, so they cancel. Now that's a manifestation of Pauli principle reformulated in terms of path integrals. In case of Ising model, there were no arrows. Just there were closed lines and they could be all oriented in one direction. But in case of Ising model, those curves were phase boundaries between spin. That's how Vdovichenko interpreted that. He said, okay, let's consider those Fermion paths and let's compare them with the sum over all spins. When you sum over all spins, you sum over all positions of boundary between spins, and that is a very well-known sum over all configuration of Ising model. And when you sum over a position of the two phases, you don't want these phase boundaries to be self-intersecting. As long as they are non-self-avoiding, you're summing over all configuration of spins. That's what she observed, and then she checked that with very meticulous arithmetics. But topological idea is exactly this. And I can tell a little story. That idea, well, I was in the Landau Institute, so I heard about that, and it was in Landau textbook after Vdovichenko, and I knew her. Anyway, this idea came to my mind, and I got very excited that that's how planar QCD should be solved by the fermions on the surface. And I even wrote the paper called QCD equals Fermi string theory, which was basically correct, except one thing. It turned out that there is no such thing as random surface because it cannot exist in 4 dimensions. So my friend Polikov stabbed me in the back at the same conference when I tried to report my discovery of Fermi string. He said he reported his Polikov measure, and he basically said that in 4 dimensions there is no such thing, because conformal anomaly. That, threw my whole theory in the garbage can together with my beautiful elves, just because I placed them on unstable surface and it just went to drain. Anyway, I told that to Ed. He came to that conference at that same year, 1980. So it was young Witten, rather a young Sasha Polikov and me, and Witten was very much interested in what we were doing, and we met in my apartment, and I spent hours and hours, got his undivided attention, and I described to him this elfin theory. He was quite understood. Being topologically minded, he immediately understood that bulletproof part of my argument. And then my theory was killed, and years later, Ed, seriously looking into my eyes, kept me asking about elf theory. And I felt very embarrassed. I said, well, Ed died. It's unstable. What can I do? He said, yes, and why? And, I thought he was joking. He was teasing me, I thought. And now I understand that he was not. He was just puzzled. How could it be that a correct topological argument failed because of something totally extraneous? And now I know why. Now I know why I shouldn't put my little elves on an unstable surface. Okay, so if you look at that picture of this self-avoiding fermionic trajectories. I was just too lazy to draw arrows, but imagine arrows. So there are all these trajectories on a disk. So they vary between each other without intersection. And if you take a red line, which is like a time slice, what you get? You will get some number of these pairs of fermions. So you will get evolution of these elves being created from vacuum elf pairs like quark pairs. Okay, so it is a history of if this is a string between quarks, quark sit here, antiquark sit here. So there are elves between, and that, Nima, is answer to your question: how could it be that there are no agents flying between quarks? In my theory, there are. There are exactly two of them. And that's how I get Lucier term later. Okay. So indeed, that anomaly is equivalent to Lucier term, as we'll see later, and that anomaly came exactly, it's proportional to two components of L. Okay. So far, topologically, that's a very appealing picture. Now let's compare it with loop equations. Let's see whether we could make it actually reproduce planar graphs. That looks like planar graphs. Topologically, it is like planar graphs, but not exactly. We want actually to have both terms in the loop equation to be what they are. We don't want just topologically be something equivalent to the planar QCD. We want exactly dynamically equivalent. We want to find what is the Baire coupling constant, what is the cutoff, etc. So let us try to go one step further.
So sorry, Sasha, but I mean, we're going to get to it. But are you saying that you have a pair of fermions living on your string, but no excitations, no string excitations?
No string excitation.
But there is a string and a pair of Majorana fermions live on this string.
That's right.
Okay.
Multiple pairs or no, sorry, all of those loops.
There are excitations,
Right.
there are vacuum fluctuations. Even heavy particles have 0-point fluctuation.
Right, but I mean, if I want to, so if I hit the string, nothing happens, but I can produce fermions that live on the string. Well, I mean, okay, we'll have to talk about the sign because
Yes, if you notice, I canceled them. Yes,
Right.
sign. I didn't expect you to notice that at this point, but yes, you see, what I'm saying is actual massive fermions are equivalent to the flat surface with massive.
Your fermions are massive or massless? They're massive.
They're very massive.
These fermions are massive.
Massive. No, what I'm trying to say is my extra term, my anomaly term, is something designed to cancel the fermion anomaly on the surface. That's why it has negative sign. Otherwise, I would have wrong sign of Lucier.
Yes, exactly.
That's what you meant, right?
Yes.
I thought about that.
Yes.
Yes. If I would literally say that I add fermion anomaly, but I'm not adding it. I'm subtracting it to get the theory which is equivalent to QCD. You see. Remember, guys, I'm not quantizing string. For me, string is not something which I take for granted. For me, string is a temporary tool. I'm solving equations. I'm finding something stringy which exactly satisfies loop equations. What I found, I take minimal surface, I place fermions, and I subtract their anomaly. That's what will solve loop equations. And because of that, my anomaly will come with different sign, and that's exactly what you need. Okay, so let us now go to the interesting part, which is how do I solve loop equation with that? Okay. Let us find the first variation of the fermion determinant. So we are now living on a flat disk, and there are fermions with variable mass. That mass is the only thing which remembers that we live on a Hodge dual surface, because that mass is proportional to square root conformal metric, and that metric is metric of the surface. But there is no kinetic energy, no connectivity, they all are gauged out. So we have flat surface and variable mass. Let's consider that theory, and let's find the variation variation of this fermion determinant with respect to area derivative. So we change the boundary. So that's our boundary. We change the boundary. How do we change the boundary? When we find the area derivative of something which is given by surface integral, we have to find variation with respect to metric, and then on top of that, find variation of the metric with respect to area derivative. So metric is absolute value of the area element, and when you find the absolute variation of absolute value by the area, you will get something like factor of 1/2, whatever. You will get normal. So basically, what I'm trying to say is when I find variation of the something depending on the conformal metric on the surface with respect to area, I get the tangent tensor of the surface. So delta variation of the scalar area, because scalar area is absolute value of the vector area element. So variation of scalar area is a unit vector times delta function. So if you would find variation with respect to scalar area, you have to multiply it by the tensor vector, which is cross vector of the two tangent components of the surface, and that will be the extra factor you need to get area derivative. So when you find the area derivative, you will get, you will trap only one fermion loop which touches the boundary, because when you find the variation of the boundary, and your determinant is sum over all paths with the weight exponential of minus metric, only the paths touching the boundary will survive. There is a formal way to derive it, but I'm giving you intuitive idea. You are changing metric in one place, so the paths which don't pass through that one place at the boundary will not change. So the paths which pass that boundary will change, and the variation of your weight exponential minus mass times length, if you find variation of that with respect to metric, you will get delta function. And that will limit you to sum over all those paths which touch the boundary. I'm just explaining that in words, but it is, of course, technically correct statement of determinant. You could do it using proper time representation of determinant, and you could find honest variation of that sum over paths. You will get the same. So basically, the statement is the following: variation of the metric with respect to sigma mu is twice t mu times delta function. So, because basically delta sigma nu is absolute value of E is the absolute value of sigma mu squared. So when you take the square root of sigma mu squared and find variation, you'll get this factor. So that's variation, and this delta function means that you will select only paths which touch the boundary. So variation of determinant with respect to sigma mu, area derivative of determinant on a surface gives very simple intuitive result. You vary this exponential minus ml, and that is this formula, and that will select only paths passing through this boundary. There will be factor minus m because of this, and there will be a product of 2z, right? Because you selected one path, and paths don't intersect. So whatever paths were inside this one are trapped. And that sum will again be z. So you will get factorization of two determinants. So if you vary one determinant with respect to area derivative, you will get sum over all paths involving two determinants because of that important property of that factorization related to topology, related to the fact that all the paths were self-avoiding. So if you select one path, it splits the surface into two terms, and all the other paths are summed inside and produce the partition function for this loop, and all the others produce partition function for the remaining part. So you get remarkable thing, you get factorization, you get z, the same z of S in, that's S in, and then I'll get z of S out. call it S2 here. So there will be one Z for this whole area outside this loop, and then another for the area inside the loop. And then there will be T mu factor sitting on this boundary. And then there will be some more all paths. And that's the basic step. We just found out that there is a planar loop equation, not quite mechanical, not quite the one which we did with mechanical, but very similar. Also planar factorization. Okay? Now, let us do one more variation. When we find second derivative, there are two terms. One term will catch two loops. So one loop will be catched. So let's find variation in point 1 on the left side and point 2 on the right. So there will be two terms. One term which will have two loops, one touching the left point, another touching the right point, and there will be three regions now. S1, S2, and S3. S1 is inside the little left loop, S3 is inside the little right loop, and S2 is the remaining area. Again, the same planar factorization. And another term will be if only one loop is caught between with two paths. So there are exactly only two terms. And as we shall see soon, the first term will identically vanish in view of the properties of the Hodge dual surface. And the second term reproduces the right side of MM equation. Now, how that happens? First of all, we want to actually consider the situation when M, the mass of the ELF, we call them ELF, well, they are tiny but very heavy. How about that? They're little ogres. Heavy ELFs, so they have a large mass. And if they have large mass, these loops are short, they're small. If you look at that, what does it mean? This is a very small window, this is a very small window, and this remaining window is almost the same as before, except these little two parts which were bitten out. And the same thing here. Not quite the same, because here I forced the same small loop to touch in two places, which would enforce these two places coincide in physical space, and that it will come later. So if mass is large, we have two terms. I call them A and B. Now, what we have in the loop equation is actually integral of the second area derivative with respect to second point. Let me show you what we actually have.
Sasha, I'm confused by something very, very basic. Physically, if you have an extremely heavy fermion, we should just be able to integrate it out, and its effect is, at least describe it another way. We should not be forced to include these super heavy objects in a description.
Oh, they induce QCD.
Yeah. Huh?
They will induce QCD.
But that's what I'm asking. So then why can't we just they'll either induce, okay. Fine. So but why can't we just integrate them out and talk about what they do without ever
but before that,
to them?
I have to deal with something which does not have the continuum limit, namely these loop equations. MM equations cannot be formulated in continuum limit. They only can be formulated in the cutoff limit, at finite cutoff. That's where I compare that with L theory. And then indeed at M to infinity, consider the continuum limit and keep working with that limit. The only reason I'm considering finite mass rather than saying, let's talk about.
But you already had a regulator in your story, right?
That's right.
I
want to compare
epsilon regulator, and then now you have this mass
it's the same.
at the same time.
I am saying they're the same. So M can compare because mechanical MM equation is under normalized. I say it is. It only makes sense at finite regulator.
That's okay. But
then at finite regulator, I compare the MM equation with ELFs at finite regulator. Then indeed, at M to infinity, see what happens with ELF theory in that limit. And indeed, there is a nice continuum limit, and that's
okay. So, but so you're matching the candidate solution to the loop equations using these massive fermions to the regulated MM
Yes.
equations. Okay.
I'm claiming that L's are regulators of the MM equation. I'm claiming that the theory with finite mass L's at large M is equivalent to regularized with split points MM equations. And then, of course, I'm going to do that. But I cannot, there is no way, that's the problem. I cannot literally, well, maybe somebody can, because momentum loop equations can be formulated without cutoff. It disappears there. So if I would be smart enough and know how to reformulate L determinant on a momentum loops, maybe they would avoid all this clumsiness. Maybe then I would just take continuum limit of L theory, go to momentum loops and compare to momentum loop equations and match exactly, and I would not need regulator. That would be very interesting exercise. Indeed.
I mean, one very basic question about matching the regulators. On the side, on the old side that you told us about, there's a regulator which is like a sort of like a point splitting, right?
Yes.
But that has some data in it, like the direction of the points. I mean, there's some
That will all
vector
cancel in
information
view of
that-
the property of the Hodge-dual surface. That's must cancel. There should be,
So
whatever kernel I get from L should
Yes.
exactly reduce to the same invariant kernel I get in MM, which is
no,
just nothing.
but I have a more basic question. In here, in the ELF theory, the only regulator is the mass M. It's a scalar. There's just
Yes.
a number M, right?
Yes.
In the regulator of the Wilson loop,
Same thing.
Well, but you have to tell me where.
No. I have to average
over.
over paths. Now, otherwise I violate gauge Lorentz invariance.
Exactly. So
So there, I average over paths weighted with some weight E minus ML, where M is some regulator. I should do the same thing. When I split points in MM equation, I
That's what you're
introduce
comparing?
some heavy
That's-
particle pass between. That's the only way.
even a few other, sorry, but also you're choosing a point along the loop. On
Oh, no,
which
no,
you're
that's
splitting.
integrated.
You're also averaging over that. So
I have to
you're-
integrate. There is no other equation.
But but I just don't remember. The previous story, was all of that part of your definition of the regulator? That you have to average and you have to split and then that,
No. Here's the point. The loop equation in QCD is valid if you take arbitrary point on that
Yes.
map, and then you find variation. But another point gets out integrated over
Yes.
the whole path. It's not like you could derive something with two
oh yeah, I
points.
understand, right.
Okay, so that's the only
Right.
equation I'm comparing here, and that equation gets satisfied.
Okay,
So there is no, but the thing which people compared was something which you take this same loop operator, integrate both points around the loop. Then you get something which looks like Laplacian operator but we found out with momentum loop equation that that's not enough. You have to keep the vector equation. You cannot really, not Navier, Young-Mills are vector equations. So you have to you have to solve all the vector equations. You cannot solve 4 equations with one scalar theory. You have to have, so the miracle here is that in spite of us using only scalar objects which live on two-dimensional surface, because we place it on a Hodge-dual surface, which knows about external geometry. That's the only reason why I get.
do you see, are we gonna see that we have to scale the coupling with M in the usual RG way in order to keep physics?
Oh, yes, I will get to that. That will be, I don't have much left. That is going to be the rest of my talk. Okay. So let us first consider this A term and see how that cancels. So when you consider this A term with 2 little windows and 2 array derivatives, what I claim happens is very simple. What I claim is happening is that if you look at that graph here, there are three factors. There is one factor which is z of this big area with two little things removed. In the zero approximation, it's just z. Then there will be two little windows. And these windows will produce some universal factors because the sum of our paths with the remaining factor doesn't depend on that little part. It's just a universal constant. So what we get will be sum of our paths, whatever, but the only thing which will be left from the path will be this T mu tensor, right? This T mu. So there, when you find the variation, you will have the factor from the internal loop, which is after integration over all loops, just some constant, but then there will be factor T mu. And the same thing on the right. So in the limit of very large mass when the paths are small, what I get is in this left term, I will get something very simple. I will get this thing. I will get this A term. It will tend to T mu times T mu times z times some constant square. That constant comes from this sum of our little paths. So there will be some constant here, but otherwise it will be T mu times T mu. Now I have to remember that I am actually my solution is proportional, as I think, to the area of minimal surface. Why? Because, well, if you have a very heavy fermion on a surface, the main term you get from that heavy determinant will be exponential of area. That's the main term. Next term will be integral of curvature. Integral of curvature is topological constant. It's not dynamical. It's just for a disk, it's trivial. So basically, for a very heavy particle living on a surface, its partition function is simply exponential of area. And then, if it is exponential of area, then we know that it is going to be replaced by area derivative. We know that this T mu is just variation of area. So that thing becomes something which we can compute. Because variation of T mu is known, it's area derivative of the Hodge-Dual area. And when we do that, we have also integral over second point. You have integral over x, where x is position of this second point. And when you integrate that, you will get exactly what the same thing we get in the loop equation, because this integral of area derivative is the same as translation invariance. So if you take integral of this thing, integral area derivative of integral of over the loop of area derivative, excluding one point, it will be the same as derivative with respect to that point. There is exact identity, which says something like that, that if you take a loop with a fixed point, then you have d mu with respect to this point plus integral d y delta sigma alpha of my functional equals 0. That's a translation invariant. When you translate the whole loop, you translate everything except that point, and then you also translate the point. So if you correctly track all that, integral over the loop Cxx of area derivatives, if you just add all the variations, then that is equivalent to this term is equivalent to integral from theta minus 0 to theta plus 0 delta x mu of s ds. There's a Mendelssohn formula by which x dot times area derivative is simply variation. So if you consider integral of variation over infinitesimal interval, that's by definition the same as this operator d mu. It fixed the delta term in the functional derivative. So delta x mu of theta times say f alpha beta of x of theta prime. What is it? It is delta of theta minus theta prime times d mu f. Because if you take functional derivative and you have local function of some other argument, then functional derivative reduces to ordinary derivative times delta function. And that's exactly, coefficient in the front of delta function is called d mu. So that's exactly what you have in the equations. So if you take the area derivative and integrate over a whole loop, it's the same as taking derivative d mu with respect to one remaining point. And that little subtlety is very important. That when you have functional derivative and you have local function, that functional derivative of local function reduces, of course, delta function times ordinary derivative. So if you want to obtain equations of motion, you will have this, and that in general can be reproduced by integral over the area derivative, and then you get that.
I have a question. I'm maybe a little confused about something. So I would have thought from your graphical description of the A term and the B term, the A term looks like the area derivative was hitting the exponential both times and bringing down S with one derivative and another S.
Yes.
That's what it looked like visually. And then the second one, which had the oval, looked like the derivative was hitting the exponential, bringing down one derivative, and then the derivative was hitting the term that came down again.
Yeah.
That's what it looked like to me, at least graphically.
Maybe.
But in the slide, it looks like you're saying the A term was this oval, or at least the.
No, B term, we'll discuss it. But the main problem about B term is that there is delta function. That's what it is.
Mhm.
I mean, the difference is that the B term connects 2 points on.
Yeah. So maybe I can write something on the board.
Yeah.
So I would have thought that something like this would be, if let's say you take that, and I'll just do in very ordinary language. Let's say we have 2x.
So one
e to the f of x, right? So this is going to be, there's going to be one term which has sort of
F
f
prime,
prime squared.
Yes. Prime times
times
F prime
e.
because there are different words.
Yes, and then there's f double prime, right?
Yes.
And so it looked to me like this thing would be more like this term,
Yes.
and this term would be.
But I computed that second term using fermionic representation. I keep switching back from one to another. I computed that term using these fermionic loops. You see, if I write it in continuum limit, I don't know how to derive it. But if I consider instead of f log that of determinant operator, then for determinant operator, I have this path integral representation, and then I could compare. Then I could find variation. That's clumsy, but maybe there is a continuum way of doing it. You should be able to do it in that continuum. Yes.
Thank you.
I only found a way to do it, with else. But maybe one could eliminate that. Just look at the result of else, which is conformal anomaly, and go to momentum.
That's what I was trying to get at as well, yeah. I mean, that the area effect is reproduce or cancel the conformal anomaly, right?
Yeah. It is counter term for conformal
Right.
anomaly. Guys, look, I barely did this. Let me say, it's hard. So help me. There must be ways of doing that. That's the main reason I'm talking with you, because you will maybe find that way. And then we will understand it much, much better. Anyway, when you do that, you will find out that because it's a Hodge dual surface for the, and this thing, by virtue of Bianchi identity, is zero, so that A term cancels. It would not cancel on any other surface. It cancels only because that integral is zero. So it's basically because of it is a zero mode of the same loop operation. Now, the B term involves something like that, right? Because the path is very short. If it is short, that means it selects the minimal surface, which must be bounded by both disks. Now, we know very well that ordinary soap film does not necessarily have that property that the surface becomes independent sum of the two. But we're not looking for the soap fields, we're looking for solution of the equations, and such solution exists. It's called Goldschmidt. It's not what's realized in nature for soap fields, but that's perfectly valid solution of the for the minimal surface, in the sense that it is a local minimum. It's just not the most topologically favorable one from the point of view of global sum. There is no such thing as global area minimization. We have we have equations of motion for QCD, not equations of motion. They are different here. So anyway, what happens here is the following. The solution which I am looking for, which is called Goldschmidt solution, which smoothly moves from the single H-shaped area into independent sum of the two, it's called Goldschmidt solution. And this little thing I drew here is what's called White's bridge. There is a theorem saying that when you say rotating, that take an oval, rotate until it becomes a figure 8. At some point, it will intersect itself. When it starts to intersecting itself, the Goldschmidt minimal surface will have this little bridge, which is almost flat. It is actually not flat in terms of external curvature. It's minimal surface, so it is twisted, of course, but it is thin. What I'm trying to say is that the surface which connects this red line and blue line becomes very small here. So physically, these 2 points are close on the surface. These 2 points which intersect in space are also close on the surface. Now, so White claimed that there is a solution which moves it. And that means that my two T-minute tensors would live, these T-minute tensors lived in principle on different places of the surface, because if there is a surface which is curved like crazy, then one T-minute was here, another here, and there was this little big bulging part. But now, if it is a minimal surface, according to White's theorem, when there is the loop is close to self-intersection, the surface shrinks and becomes locally small. And that means that these two T mu would be a similar physical location of the surface, which means they will be the same, and then we'll have T mu times T mu, and that will be delta mu. So it will be universal delta mu constant. And that is, by the way, also property of the Hodge dual surface, because in case of Hodge dual surface, both these T mu are proportional to these Hopf matrices. They are anti-self-dual, so there's only three components. There is this basis of three-dimensional basis of self-dual and anti-self-dual tensors. There is 6 components in general for antisymmetric tensor, but there are 3 and 3. Each one only 3 components: self-dual and anti-self-dual. So what will happen? I can prove that reduces to -1/4 delta A nu, and that's what is needed to get the second term of the second term. I'm describing it here. That is what is needed to get from the B term, the second term, the actual right side of the MM equation. So we get exactly this delta alpha nu, and then there is nothing else. Everything else is covariant. And then we have this another theorem, which is almost trivial for a physicist, which says that the physical distance in space, embedding space, is always larger. I'm sorry, distance on the surface is always larger or equal than distance in physical space. If you take a very strong rubber band and take a little balloon and tie it, then of course it will be tied in physical space also. That's what I'm saying. So if the distance between 2 points on the surface is small, measured along the surface, then of course it will also have to be small in physical space. Because here we didn't have this delta function in physical space. We only have some of our paths with exponential of L mass times distance measured along the surface. So if we take large mass, that distance measured along the surface becomes small, and that forces us to make something equivalent to 4-dimensional delta function. And that's a matter of normalization, how we well, actually, very simple. If you compare these two distances, then that's exactly what you get, because if you integrate that distance, it's massive exponential. It's very trivial to integrate in 4 dimensions and get normalization. Okay, so we get the right term. Now we get some constant in front. We didn't just get the right side of the loop equation. Equation is nonlinear. We get some factor lambda, and that factor lambda is that little thing. Remember this loop normalization of the W, because W is normalized to 1 at 0 mass. W is normalized to 1 at shrunk loop. So if you turn out, if you move out that normalization factor, you will get square of that here. Right sign, correct sign, which is nice. It would be catastrophic if the sign would get wrong, and then have an arbitrary small constant. That's a normalization of our path integral. That's something which we could always add. And that means that we have the family of solutions with parametrically small constant.
Sorry, but I presume that as m goes to infinity, you should see that you have to scale lambda to 0 or infinity. I don't know your conventions to according to the beta function, right? You should not just be able to say
No, that's not there yet. I only say that the right side of my equation will have this dimensionless coupling, which is lambda 1 squared, and everything else.
But you should not be able to send m to infinity without sending lambda to 0.
That's right.
Yeah.
So I'm doing what physicists do. I keep it prepared to be sent to infinity, keep lambda prepared to be sent to 0, then I will do simultaneously. That's called normalization group.
Yes, but you haven't said that yet.
Well, I would say geometrically, m is already very large. So all the power-like terms of m are neglected. But logarithmic terms are not yet summed up.
Okay.
Yes. It is, I agree, it is a little shaky argument. How I couldn't really say it is a delta function, because if I say, I should also say that lambda is 0. So it is a delta function with the width m, and lambda is not quite 0, but something very small. And I have to sum up the terms before I normalize and say how they are related. But we know, once we have that equation, we discussed that in the previous lectures. Once we have this MM equation regularized with some regulator, we keep the regulator finite, we sum up, and we have small coupling constant, finite regulator with some graphs, and then we get exactly the same graphs as same terms as everybody else gets in planar QCD. We put on the same normalization group, we would sum up the terms, and then we would get the same result. We will get this result that our effective lambda QCD for that theory will be r lambda raised to these universal powers, because that's what we get from the planar graph. So what I'm trying to say is the rest is universality. Once we get something which in the local limit becomes equation, and we will iterate in coupling constant, then we will get planar graphs, and each planar graph, when we tend the cutoff to infinity, will become some power of log, and the coefficient, of course, will come out exactly as in QCD, because those coefficients follow directly just from the structure of equations. It's 11 or 51, it's not something extra, it is what follows from combinatorics of these planar graphs. So what I'm trying to say, though of course I haven't proven it, I'm just presented to you the arguments. And I hope that for physicists, these arguments would be tempting. It's not convincing, but at least tempting, suggestive. The argument is that indeed I have something which could be regarded as regularization of the equation. And then I take that something which at the level of substituting in the equation and naively tending cutoff to infinity gets this singular delta function in the equation. So I have regularization of the equation. Now, that regularized theory, as I will describe you in the next lecture, I could solve in continuum limit. I could remove regularization now once I have the solution. That's what I'm trying to say.
By the way, what's the lambda to the negative 51 over 121? That's the two-loop beta function?
Yes.
Okay. But there's a whole.
Oh, the rest is non-universal. The rest is could be just redefined. If you redefine coupling constant,
I'm not so sure. I mean, of course.
First two terms are universal.
Well, they're scheme independent.
Yes.
But you're specifying a particular.
Oh, no, there
so
must be some,
so,
no, there is of course universal number, magic number, which people measure in lattice QCD. I don't know how to do it, no.
Yeah, I'm just saying that you have a specific regulator. Once you specify the regulator, you're
That's
done.
right. You are right. In my theory, theoretically, I should be able to compute that particular number.
Yes, yeah. That's right.
But I could say something else. I could take a bypass. In my particular theory, I could compute the string tension. Don't need to
Oh, no, it's
think
fine.
about
I was just trying to understand why you're stopping
definitions
at
of
that
lambda
point.
QCD, because
Yeah.
in my theory, I
that's
could
fine. No,
find the
that's right.
spectrum. And that's the shortest path to computing these universal numbers.
Well, I mean, really, you should find some way to, yeah. The lambda depends on m. Your lambda has to depend on m in such a way that physical quantities are independent of.
That's
m.
right. If I tend my lambda to 0 and my m to infinity, that cancels, compensates, and that lambda remains.
Yes. I just wanted to understand why you're just including that one. But you're just.
No, I'm
the
saying
first-
that
the first
this
term
is
of the
enough to
function.
get it finite.
Right.
But if you change the scheme, there will be some constant
No,
in front.
that of course, yeah. I just wanted to know why you're stopping at two loops.
So I can summarize it now. And so Majorana fermions, let me do it step by step. Majorana fermions on a Hodge dual minimal surface precisely mimic gauge invariant loop dynamics of planar QCD. Topologically, yes, dynamically, I almost proved it in front of your eyes, but if you look at my paper, which by the way will appear today, the latest edition where I finished my computations. But there exists an old version in archive, but I would want you to see only the one which will be released today because there is a final beautiful formula for the energy, for the mass spectrum. So anyway, I have proven to you at the level of physics hand waving that Majorana fermions on a Hodge dual minimal surface precisely mimic the gauge invariant loop dynamics of planar QCD. There are topological cancellations. That is a most, I would say, the bulletproof part of the whole construction. Indeed, that topological cancellations exist and cancels non-planar graphs on a surface. And now this geodesic localization and large mass limit, the White's bridge and geodesic inequality generate the necessary four-dimensional contact term in the loop equation. And then basically we are inducing QCD. We are making effective, we're taking massive fermion theory And in the limit, when mass goes to infinity, the scale is much smaller than this mass, and we have effective Lagrangian, which is F mu squared. I didn't do it this way, but instead I reproduced the loop equation. But philosophy is the same. If you take very heavy fermions and consider, in heavy, what's induced is you have heavy fermions, and gauge fields are the Lagrange multipliers nullifying their currents. You have term A mu, G mu, where G mu is a current, vector current of the quarks. So you have a free fermions with restricted, which are strictly restricted to the gauge invariant sector. So free fermions with locally vanishing gauge currents. And that theory, if you integrate out fermions, produces for this F mu effective Lagrangian, which makes this Lagrange multiplier A mu live objects. That's the idea of induced PCP. So we have similar thing here. We have heavy fermions, and when we integrate them out, we get this effective Lagrangian, this Liouville term, which makes the surface alive. And that is exactly what we get. We effectively induce, well, I would say this heavy fermions induce planar graphs on the surface. And that is like F mu squared getting F mu squared by integrating out heavy fermions. So that's a similar philosophy. Take heavy fermions and they induce gauge theory. And that's what happens here. Now, to answer physical arguments by Newman in the other lecture, he says, in relativistic theory, there is no such thing as an instantaneous action on distance, so there must be some particles propagating between quarks mediating this force. And my answer is, in my theory, yes. Else are these particles.
Your particles are massive. There should be,
That's right,
yeah.
but massive particles still have 0-point fluctuation, never mind what.
right, but we should not, anyway.
No, you
This
want
doesn't
light,
decide, huh?
you want
Yeah.
light particles.
Yeah, I want light part, and we'll come back to the sort of physical argument. Well, anyway, we can have the physical discussion.
Because I'm going to
later,
consider
yeah.
actual solution for the string when I will derive the spectrum. That's the proper moment to ask these questions. Where are all these waves
Exactly,
which would do
right.
that?
You
Yes.
see, what I don't understand is why you're so against these waves. Like,
Because I
but-
don't see how these waves would not lead to the same effects which kill the fluctuating surface.
Mhm.
You see, if there are actually physical fluctuations all over if there are waves going like that, that's
No, but-
fine.
but-
But if there are waves all over the two-dimensional surface, that's what kills it, right?
No, I mean, but sorry, not only.
Fluctuations.
Yeah, but it only kills it if it's two things. It's the string being infinitely thin and having waves on it, which kills it. After all, you can have a Nielsen-Olson vortex, any kind of cosmic string. These are strings. They definitely have waves on them. They're perfectly healthy, okay things, right?
Because they are
things
only
that,
imitation of the string. They are actually configuration of the field.
they're configuration of fields from far away. They
Fluctuations
look
of
like
fields
strings.
don't
Yes,
kill it.
that's right. Yeah,
Geometric
right, right.
fluctuations of physical shapes. That's what kills it, right?
But I'm saying that there's nothing wrong with a long string. A very long string, which is much longer than its thickness, so the thickness doesn't matter. This object has waves on it, everything is fine. This is what we kind of normally think of.
And where is this
right. Yeah.
conformal anomaly?
Sorry?
Conformal anomaly which kills it. And tachyons which kills it.
You don't see it here. You don't see it, you see those things when the string becomes short, right? Because all of those things are relevant when the string is long. For example, the tachyon
Yeah, but
is
I don't
relevant
want to
because,
make that,
right.
no, but the WQDB limit, I agree. But I'm trying to go beyond that.
I understand, but I'm saying that the sort of aspect of QCD, I mean, just repeating again, the kind of reasons that we think there's a string with fluctuations on it is if we imagine we take our two favorite heavy quarks, we pull them apart. We have this picture of the string between them. Then if I keep these heavy quarks apart and now I wiggle one end, the other end doesn't instantaneously move, right? There's some wave that propagates down.
My
and moves up, yeah.
quarks
Right.
are dynamical objects. And my
right.
whole quantization comes because I'm quantizing that motion.
we should be able to describe in your theory what would happen if we added non-dynamical source.
Yeah, I
ports.
can
Yeah.
add mass term to
Yes,
my
right,
action.
right.
I don't want to pretend. No, I can add.
Yes, so then if we do that, then we can have these big heavy
Okay,
ports and then.
let's postpone that discussion.
All right, yes, right,
Yes.
right.
But anyway, what I'm trying to say is that those Liouville terms which I added to cancel
Yes.
fermionic zero modes,
Yes, yes,
because fermionic zero modes was called negative, wrong sign, so what I added therefore is positive. That is a perfect imitation of the
True,
Liouville term.
yes, I agree that the Casimir energy of two massless fermions is the Casimir energy of two massless bosons. That's, I agree with that.
Well,
All right,
that's not
yes.
how I derived it.
No, I
but
understand,
In
I
the
understand.
end, it
Yes,
is,
yes,
yes.
right. Okay.
Guys, well, I didn't really take too much of your time today, but I think I explained the most important part of my theory. So I really want you to have a few minutes of open discussion and earn this bottle. Maybe at the moment, I would say, Nima, I haven't heard really tough questions.
No, I think we should not give it, I think we should keep the bottle for next week and maybe let people cogitate a little bit. And, because, yeah, we can't just give it away, huh? No, just,
No,
just,
you
just
came
this,
close.
this.
You
bottle.
came close. I will give you a sniff.
Just to motivate you to do a little better next time.
Yeah, right.
Exactly.
You could read it, you could.
I don't think
photos,
anyone,
that-
honestly, I'm sorry,
allowed to
Daniel,
drink
but
the bottle.
I mean,
Yes.
your questions were okay, but I don't think
No,
he's
no,
deserved it yet.
no.
I think he would agree.
I would agree with that.
Yes,
I would
yes,
agree
he
with
would
that.
Okay.
So I think we have to have proper urging.